Well, hey guys, welcome back. What we're going to focus on this time is how to work on using percent composition, right, to determine things like empirical formulas and then ultimately molecular formulas. So a couple things. First of all, we're going to do some step-by-step stuff just so we can iron out the actual calculations themselves. But I want us to go beyond that, and so I'm going to try to provide some context so that you understand sort of the purpose of what we're doing. I want you to move beyond just simply being able to do the calculation and not really having any sense of what it actually means. All right? So first of all, percent composition. Here's our step-by-step, and I want you just to write these steps down. If you need to pause to slow me down, fine. But write these steps down in your notes so that when I do the example on the following slide, you've got those steps to refer back to. All right? So step one is you find the molecular mass in the same way we've been doing. Step two, find the mass of the individual elements in the formula. And step three is to divide the individual mass by the total mass and then multiply by 100. And that's that converting to a percent thing. Okay? You always multiply by 100 to convert a decimal to a percent. So with that in mind, let's try one together. So again, if you need to pause and go back, make sure you write those 3 steps down because those are going to be important. But in this example, we want to determine the percent composition for each element in sodium carbonate. Now, sodium, as you guys know, is Na+, carbonate is CO3 2-. I did not give you the actual formula for this, and that's because you need to remember how to do this. This is something that is not going to go away. All right? So let's write our formula first. We have a 2 on the carbonate, a 1 on the sodium, which means I'm going to write Na2 and then 1 carbonate involved. So that is our formula. Now, what I need to determine for sodium carbonate is the total molecular mass. All right? So I've got 2 sodiums, so I'm going to go 2 times 22.99. And of course, that 22.99 number comes from our periodic table. So that's 2 sodiums plus 1 carbon plus 3 oxygens. All right, and when I do that, my molecular mass should come out to 105.99 AMU. All right, and if that was molar mass, of course, that'd be 105.99 grams. All right. So what I've just figured out there is my total mass. Now, to determine my percent composition, if you guys remember, I need to then find the mass of the individual elements in the formula. So I have 3 elements. I have sodium, I have carbon, and I have oxygen. All right? So if I want to determine my percent that is sodium, I'm going to go 2 times 22.99. All right, so that is the mass of just the sodium in that formula. Okay, so that would be the mass of the individual element sodium. I'm going to divide that by the total molecular mass, which is 105.99. And then, of course, that will give me a decimal. To turn that decimal into a percent, I multiply it by 100, and that should give me 43.48% sodium. All right, so that is one of my 3 elements. The next one is carbon. I only have 1 carbon, so it's just going to be simply 12.01 over 105.99 times 100, and that should give me 11.33% carbon. And oxygen then is going to be 3 times 16 over 105.99 times 100, and that will give me 45.29% oxygen. Okay, now, just a quick side note, making sure we're staying on top of things. Notice that I used the mass of 16 for oxygen, right, rather than the diatomic form. We only apply that Brinkelhoff diatomic rule when oxygen is by itself. Oxygen is part of a compound, so I don't need to worry about doubling the mass. Right? Now, quick way to check my work. Do these add up to 100%, or at least reasonably close to 100%? And the answer to that is yes, they do. All right, so that's an easy way to quickly check your work on percent composition problems. If your individual percents do not add up to 100%, then maybe you did something wrong. Okay, now keep in mind with rounding and sig figs, sometimes we may not end up with exactly 100%, but something pretty darn close to it. Within a fraction of a percent is where we should end up. Okay? So that's percent composition, and I feel pretty confident that all of you will be able to do that without too much trouble whatsoever. So when does this get more complex? That is when we are using percent composition to determine an empirical formula. So let's do a quick definition. I know we've been exposed to this already, but an empirical formula is simply taking our ratio of the different elements in a molecular compound and reducing it to their lowest whole number ratio. So first of all, what type of compounds are always empirical? That would be ionic. Okay? Molecular compounds or covalent compounds are not always in their lowest whole number ratio, but sometimes knowing their empirical formula is still beneficial to us, and we'll see why here in just a moment. But we have benzene, for example. The actual formula of benzene is C6H6. That's 6 carbons and 6 hydrogens bonded together. Now, if I wanted to know the empirical formula of benzene, I'm just simply talking about the ratio of carbon to hydrogen. Now notice that there's 6 of each. Now, so that reduces to a simple formula of 1 to 1. So the empirical formula for benzene is just CH. Every 1 carbon, there's a 1 hydrogen to match it. All right? So it's just like taking 6 over 6, right, which gives you a value of 1. So it's a 1 to 1 ratio. Ethane, on the other hand, has a ratio of 2 carbons to 6 hydrogens. So that is the molecular formula, right? Sorry, I am having difficulty writing. Molecular formula. Okay, C2H6 is the molecular formula. Now, that ratio, 2 to 6, can be reduced to 1 to 3. So this is my empirical formula. All right? So that's what we mean when we say empirical formula. It's just the ratio of one type of atom to another. Okay? So how are we going to use this idea of empirical formulas with percent composition? Hopefully you're asking yourself that question, or asking that question as we go. So here's what it looks like, and this is where things get a little more complex. Not so much in difficulty, but in that there's lots of steps involved with this. And they do make sense, and this is why I said I wanted to try to create context. So that it's not simple memorization for you guys, but understanding what's actually happening. All right, so if you know the percent composition for a compound, okay, here are the additional steps we can use to determine what the empirical formula is. So let's say we didn't know the actual formula of this compound. We don't only know its percent composition. All right? So first, step 1 is to divide each element's percent composition by its atomic mass. So again, I want you just to write these steps down, even if they don't entirely make sense to you out of context. Put these steps in your notes so that we can refer back to them when we do an example problem here in just a moment. Step 2, you're going to take your smallest answer from step 1. So again, you're going to have multiple elements that you're doing this for. You're going to take your smallest number and you're going to divide each of the other numbers by it. Again, this will make sense in just a moment once I put it in context. And 3, you're going to use the numbers to determine the ratio in your empirical formula. And then we can write our empirical formula from that. Okay, so again, make sure you write these steps down. If you have to pause this video, pause it, get these steps written down, and then use them as a reference for the next example. All right? So we have an empirical formula for a compound that contains 25.9% nitrogen and 74.1% oxygen by mass. All right, so we know that percent composition already. Right. What we don't know, we know that it's some sort of compound formed between nitrogen and oxygen, which could be lots of different compounds. There's lots of ways nitrogen and oxygen can combine molecularly. All right? So we're going to use this information to determine the empirical formula, at least the ratio of nitrogen to oxygen. Okay? So how we do that, remember, step one, divide each element's percent composition by its atomic mass. So let's start with nitrogen. The percent composition is 25.9, right? Now, so that is nitrogen. The molecular mass the atomic mass of nitrogen is 14.01. Now notice again, I'm not using the Brinkelhoff, the diatomic mass. This is nitrogen as part of another compound, so I'm not doing N2, it's just N. All right, and when I do that, I should get a value of 1.85. Okay, so that is for nitrogen. I'm going to do the same thing for oxygen. I'm going to go 0.1% over 16.00, and that gives me a value of 4.63. All right, so I've done step one. I've divided the percent composition for the element by the mass of that element. Now again, so let's think about what we just did. Why did we do that step? All right, so the percent composition is a function of mass and abundance in a formula. All right, by dividing by the mass, we're essentially just getting an abundance ratio. So this is an actual ratio. All right, now that's an ugly ratio. That's really difficult to look at those two numbers and determine how many nitrogens to how many oxygens we have. Okay, so what we do is we want to put these in whole numbers because molecules form in whole numbers. So step two is we're going to take our smallest answer and divide each of the others by it. So I'm going to divide 1.85 and 4.63 by 1.85. Okay, and what I get is a ratio of 1 to 2.5. Now, here's one thing to understand. We need to have whole numbers. Okay, what we've done is we've turned the 1.85 into a whole number. We've turned this into 2.5. Now, when we do this step, right, a couple things can happen. One of those things can be we get two numbers that are both whole numbers, or at least really close. So, for example, let's say this came out to 2.96, right? I would just make that 3. Okay, what happened here is this came out to 2.5. I can't round that much with this type of question. So what I'm going to do is, because this is halfway in between 2 and 3, I'm going to multiply these both by 2. So I'm going to make this a 2 and make this a 5. All right? So what we've just done is now we know our empirical formula. The lowest whole number ratio is 2 to 5. So it's going to be N2O5 is our empirical formula. So let's walk back through those steps. Okay. We divided each element's percent composition by its atomic mass. So I went 25.9 over 14.01 for nitrogen, 74.1 by 16 for oxygen, and I got 1.85 and 4.63. I then took the smaller of those two values, which is 1.85, divided both numbers by 1.85, and I got 1 to 2.5. Because 2.5 is not a whole number that we can easily round, right? We need to then turn these both into whole numbers by doubling both of them. And that gave me a 2 and a 5. So that's 2 nitrogens to 5 oxygens. All right, so I know that may seem like kind of a lot of steps and a little bit convoluted. Just need to practice, just like everything in chemistry. The steps themselves really aren't so hard. You just need kind of repeated exposure to it. So you should get most of that with the ChemQuest, and of course we'll do some extra practice, kind of like we did with the mole stuff. All right. So just a heads up, we are going to learn how to go from empirical formula to derive the actual molecular formula as well. But we're going to add that kind of together in class. I feel like this is enough to be getting on with for now. All right. So make sure you walk in the door tomorrow with the step-by-step for how to do percent composition and then how to go from percent composition to empirical formula. All right. Keep after it.